Hey everyone. So the other day, somebody asked me about how I realized that this is a dynamic programming problem. So today I'm going to talk about dynamic programming and let's see an example. So first of all, I wrote down the feature of dynamic programming. So what is a dynamic programming? So number one, so divide a problem into small parts. And the second, keep results to reuse them later like a node. And three, use the results you have when you face the same calculation. Yeah, but I think nobody understands what is dynamic programming if you don't know it. So let me share one example in daily life. This is an image of dynamic programming. So there is a math question, 32 multiply 18. So what is the answer? So if you are good at mathematics, so you can immediately answer it. And the answer is 576. Yeah, it's easy question. But so what if we face the same numbers multiply 4? So that means 32 multiply 18 multiply 4. So it's a 2304. So I mean, we means human. So human already knew 32 multiply 18 is 576. So naturally, we calculate like actually this one is going to be like 576 multiply 4, right? Because the calculation of 576 multiply 4 is easier than like 32 multiply 18 multiply 4. And it's time saving because we already calculate like this part. So we can naturally calculate a math question with like a previous result, this one. But the computers don't work like that. So even if they already calculate like a 32 multiply 18, they when they face the 32 multiply 18 multiply 4, they calculate from beginning to last. So this question, so I use three numbers, but what if the numbers are like 1,000 or millions? So it's very time consuming, right? So that's why we have to keep the old results for computers like a node. So that's why I said like a node. Yeah, and that is a basic image of like a dynamic programming. Okay, so let's see the dynamic programming with a real algorithm. So this is a very famous algorithm, Fibonacci number. So I don't explain the Fibonacci number deeply, but so Fibonacci number is like a total number of previous two numbers. So let's say n is 4. Fibonacci number should be 5 because previous two numbers. So look at the previous two number. So total number of previous two number 2 plus 3 should be 5. So that's why Fibonacci number is 5 in this case. And n is 5. So Fibonacci number should be 8 because the total number of previous two numbers should be 8. So now you can guess n is 6 easily. So Fibonacci number should be 5 plus 8 and 13. Yeah, that's easy. And this is the entire program of Fibonacci number. And I wrote down the tree. So this is a n is 4 case. So from uh, from the root, so we have two calculation like n minus 1 plus n minus 2. So from 4, so 1 is 3, so that is n minus 1. So for n minus 2, we have to calculate n is 2. So let's move down 3, left side. So again, we have a 2 calculation, like n minus 1, 2, n minus 2, 1. And let's move down left side. Again, we have a 2 calculation, like n minus 1 and n is 1, so n minus 2, so n is 0. And we do the same thing on the right side. So overall time complexity should be, so we every time we have 2 calculation and n time. So that's why overall time complexity should be 2n. So n is like a height of 3 in this case. So that's very time consuming because look at this subtree and this subtree. So these two subtrees are exact same structure. So the root is 2 and 2, and the left side is 1 and the right side is 0, and the left side is 1 and the right side is 0. So actually we do the same calculation again and again and again. So this is a small tree, but what if like if it's 100 or 200 or 1000, something like that? We can guess easily, like we do the same calculation like again and again. So that's why very time consuming algorithm. So that's why we need to keep the like old result and then use them when we face the same calculation later. So that is like a dynamic programming. And so in this case, let's see how it works. So f1, so when n is 1, less than 1, or less than or equal 1, return 1. So this Fibonacci number return 1, and when n is 0, return 1. So if n is 2, so Fibonacci number should be previous 2 number, 1 plus 1 and 2. And this is 1, this is 1, this is 1. And when n is 3, total number of previous 2 number should be 3. And when n is 2, 1 plus 1, then 2. So when n is 4, previous total number of previous 2 number should be 3 plus 2. And Fibonacci number should be 5. And yeah, looks good. So next, let me improve this algorithm. This is a dynamic programming version of Fibonacci number. So first of all, I create a node list, initialize with all 0, multiply 101. So this is a like a input number plus 1. And in the function, if current number is 0, in that case, that means that is a new calculation. So we have to calculate n minus 1 plus n minus 2. But every time we keep the result to the node list so that we can prevent the same calculation later. So in the end, I timed the algorithm and got like a 0.00011 something. So very efficient because we can improve the time complexity from 2n to linear time. So if we have a node list, we calculate each number once. So that's why time complexity should be on. And I put 100 in a previous function, previous algorithm, not dynamic programming version. And actually, I didn't get the answer more than 10 minutes. That should be out of memory or something. I'm not sure, but I didn't get the answer. But in this case, we get the answer correctly and good time complexity. We can improve the time complexity to linear time. So that's why, in this case, dynamic programming works for this question. Okay, so let's talk about how I realized that I can solve this question with dynamic programming. Now, actually, in my opinion, there are hint keywords for dynamic programming. So if you find this keyword, there is a possibility that you can apply dynamic programming to the question. So the keyword is like, you need to count distinct way, distinct path, or distinct combination. If you find this kind of keyword, you may apply the dynamic programming to the question. Or if you find like a minimum number of something, or maximum number of something. In that case, yeah, there is a possibility that you can apply dynamic programming to the question. So let's see the real problem. So this is climbing stairs. So you are climbing staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. In how many distinct way can you climb to the top? Yeah, so you can find distinct ways, and every time you can take 1 step or 2 steps. So yeah, I think there are many ways to reach the top, and you have to count the distinct ways. So in that case, you may apply the dynamic programming to this question, or so this is a coin change problem. So you are given like a coins 1 to 5 and amount 11. So you have to make 11 with these coins. So like a 5 plus 5 plus 1, something like that. So in this question, the question said like a return fewest number of coins that you may need to make up that amount. So yeah, fewest number is similar to like a minimum number of coins. So yeah, in that case, there is a possibility that you can apply the dynamic programming to the question. This is an approach when you think you may apply dynamic programming to the question. So step 1, try brute force first with drawing pictures like a tree. So important thing is that drawing the picture. So I think it's hard to think about a question only in your head. So drawing the pictures are very important point. So you think like I'm a super engineer because I directly explain the efficient way to solve the question in the video. But before I film the video, basically I try brute force first, then think about the efficient approach to solve the question. And step 2, the finder duplicates subtrees or the same result in the tree. So as I explained earlier, so do you remember like a Fibonacci number? So there are a few like duplicate subtrees, right? So in that case, yeah, there is a high possibility that you can apply dynamic programming to the question. So then step 3, yeah, apply dynamic programming to the question. So yeah, let's see the real example. Okay, so let's see the real example on this question. So climbing stairs. So you are climbing a staircase. It takes n steps to reach to the top. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? So let's see the example. So n equal 2, output is 2 because there are 2 ways to climb to the top. So 1 step and 1 step and 2 step. Yeah, that's easy. So yeah, let's think about yeah, let's say n is 5, so top is 5. So in that case, so we can find like a distinct way or something. So we think like there is a possibility that we can apply dynamic programming to this question. And first of all, let's think about the brute force way. So start from here. And every time we can like a step like a 1 or 2 steps. Okay, let's go down the like a 1 step. And next, we can step 1 step or 2 step. In that case, 1 plus 2 and 3. And okay, let's move down the left side. If we take a 1 step, and then again, we can reach 3, or if we take 2 steps from 2, that should be 4. And then again, if we take a 1 step, that should be 4. And if we take 2 steps from 3, that should be 5. Yeah, we did. So sorry, n equal 5. And yeah, we reach top stairs. And then let's continue. So if we take a 1 step, we reach 5. and like this is over 5. And yeah, let's think about here. So if we take a one step, we reach 5. If we take a 2 steps, we over like a stair 5. And then let's think about here. So if we take a one step, that should be 4. To take a 2 steps, that should be 5. And again, if we take a one step, that should be 5. And take a 2 step, that should be 6. Yeah, and yeah, that's it. And so let's think about when we take a 2 step from the first step, first place. In that case, again, we can take a 1 step, so that should be 3, or 2 steps, that should be 4. And then take a 1 step, oops, and 4, and 2 steps, 5. And again, take a 1 step, 5, and 6. Then yeah, let's think of it here, and take a 1 step, 5, and take a 2 step, 6. Yeah, so 3 is like something like that. And did you realize that there are many duplicates? Yeah, a little bit messy, but you can find a duplicate subtree. So first of all, yeah, the largest duplicate subtree should be here and here. Oops. So let's see. So top from root, like a 2, 2, and 3, 4, 3, 4, 4, 5, 5, 6, 4, 5, 5, 6, and 5, 6, 5, 6. Yeah. These subtrees are exact same structure, right? So that's why actually we don't have to compute or recalculate this part, because we know that the result of this subtree. So, and then actually there is another duplicate subtree. Let's look at so first we move down on the left side, so we calculate this area first. So now in that case, when we finish this subtree, so we know that our result of this subtree, so 3, 4, 5, 5, 6. So let's look at oops, yeah, sorry, a little bit messy, but let's see this area, like a 3, 3, 4, 5, 4, 5, and 5, 6, 5, 5, 6. They are exact same structure. So and then so we don't have to think about this parts actually, because we already had a result of this subtree, this one. So if we take a note, we don't have to calculate again. And then actually there are one more duplicate subtree. Okay, purple. And look at this small subtree, 4, 5, 6. So, and look at this subtree. So, yeah, as I told you, we go down on left side. So, when we reach the this area, we already had a result of this subtree, and we can find the exact same subtree here, like 4, 5, 6, 4, 5, 6. So we don't have to calculate this subtree because we already have a result. Yeah, so that's why we only calculate this area and 5, 4, 2, and something like that. And when we reach like a 2, 3, 4, uh, we can immediately return the result of the subtree because we already have had the same structure subtree in our node, so we can access it and immediately return. So that's why this question roughly time complexity should be order of n. Yeah, so that's how I apply to dynamic programming to the question. Okay, so yeah, that's hard, right? This is a easy question, but if you think about this question in your head, only head, yeah, it's gonna be tough. So that's why I recommend you drawing the picture like this and find a duplicate subtree or like a same result. Yeah, so that's all I have for you today. So if you like it, please subscribe the channel, hit the like button, or leave a comment. I'll see you in the next question.